Settle into whatever position you will be sleeping in. Let the bed take your weight. There is nothing to do here, and nothing to get right. Take one slow breath in. And let it go without hurrying it. Now bring your attention to your feet. Let them be heavy and let them be still. Let that heaviness move up through your ankles and your calves. Your knees, your thighs. Notice your hips resting into the surface beneath you. Let your back soften all the way up from the base of your spine. Your stomach loose. Your chest rising and falling on its own. Let your shoulders drop away from your ears. Let your arms be heavy, down through the elbows into your hands. Let your fingers uncurl. Now your neck, let it lengthen a little. Unclench your jaw, let your teeth come apart. Soften your tongue and the space behind your eyes. Let your forehead smooth out. Your whole body, heavy and warm and still. In a moment, there will be a story about steel. You do not need to follow it. You do not need to remember any of it. Let it go on in the background, and let yourself drift whenever you are ready. The pattern was the oar. On the broad side of a good old sabre, the flat face between the edge and the spine, there is a pattern that looks like moving water. Fine pale lines curl through a darker ground, sometimes running the length of the blade in long parallel waves, sometimes gathered into rungs that climb toward the point like the treads of a ladder. Smiths and buyers called it the watering. It is not decoration applied to the surface. It is the inside of the metal, brought up into view by wiping a mild acid across the polished face, so that the acid bites some of the metal harder than the rest, and what was hidden comes up as light and dark. Grind a layer away, and the pattern is still there, shifted a little, the way the grain of a board shifts when a carpenter takes another pass off it. Acid reveals a difference in how the carbon in the steel has arranged itself. Steel is iron with carbon dissolved in it. When there is a great deal of carbon, more than the iron can hold once it cools, the excess comes out as a hard mineral called iron carbide. In these blades, the carbide is not spread evenly. It sits in layers, coarse particles in one layer and much finer particles in the next, and the layers lie flat along the blade like sheets of paper stacked through it, about a 20th of a millimeter from one sheet to the next. Acid attacks the coarse layers and the fine layers at slightly different rates. Those bands also wander up and down inside the metal, and as the smith grinds the blade thinner toward the edge and the point he cuts through them at different depths. That is why the pattern looks like water and not like stripes. Working out that much took European laboratories roughly 2 centuries. 2 harder questions took longer. Why are the bands there at all? And why did a craft that made them reliably for something like 1,000 years stop making them and prove so hard to restart? 2 different things are now sold under the name Damascus steel. Walk into a knife shop today, and the blades sold under that name are pattern welded. Bars of 2 different steels hammered together while red hot until they fuse into one bar, then folded, twisted, and ground, so the layers show on the surface as a visible figure. That technique is old, practiced across Europe and Asia for something like 2,000 years. A historical Damascus blade is a different object. It was forged from a single piece of steel that had been melted and frozen solid in one lump, with no welding in it anywhere. The usual explanation of the name is that such blades reached Europe through the Syrian city, though the derivation is disputed, and rival accounts trace it to the Arabic root for watered or to a swordsmith called Damascus. The steel was certainly never made in Damascus. It was made in South India and Sri Lanka in the form of small cakes. Ore and charcoal and a quantity of green plant matter went into a crucible, a sealed clay pot built to be heated until whatever is inside it melts. The pots used for this were about the size of a fist and held somewhere near 400 grams of iron. The pots were packed in rows of a dozen or 15 into a pit lined with ash, and fired for hours at temperatures above 1,300 degrees Celsius. That is hot enough to melt steel rather than merely soften it. Elsewhere, iron was ordinarily worked in the solid state. A spongy mass of metal came out of the furnace mixed with slag, the stony waste left over from the ore, and the smith beat the slag out with a hammer. Metal in that process never became a liquid at any point. Inside the sealed pot, the iron melted, and the leaves and stems sealed in with it burned to carbon, and the carbon dissolved into the molten metal. Crucible workers insisted on letting the pot cool slowly. As it cooled, the melt solidified into a cake of steel, a disc about the size of a hockey puck, carrying between 1 and 2% carbon by weight, an average near 1.5. Ordinary carbon tool steel today sits near 1%. Above that, the metallurgy turns awkward. Solid steel is a mosaic of tiny crystals, and leftover carbide tends to settle out along the seams between them, wrapping each crystal in a shell of brittle mineral. Steel at 1.5% carbon is difficult to forge and easy to ruin. Forged correctly, though, the same steel puts its carbide into bands rather than shells, and those bands are the pattern. Cakes of this steel were an export commodity. A South Indian word for it is Ukku, and the word that reached English is woots, first written down in that spelling in a paper read to the Royal Society in 1795, probably as a mistranscription. Broken crucibles dug up at Kojumanal, a site in Tamil Nadu in southern India, show the industry already running in the 3rd century before the Common Era. By the 1600s, cakes were leaving the Coromandel coast, the southeastern shore of India, in tens of thousands, bound for Persia and the Arab world, where the smiths who forged them into blades lived. Steel and swords were made 3,000 kilometers apart. The men who bought the cakes and the blades were connoisseurs. In 9th century Baghdad, the philosopher Al-Kindi wrote a treatise called On Swords and Their Kinds. It separates swords by what metal is in them, crucible steel or plain iron, and it handles separately the blades built by welding pieces of different metal together. Then it sorts each kind by where it came from, across Western and Southern Asia and into Europe. It divides them into the antique and the new, where antique is a judgment about quality rather than about age. Watering is described in real detail, because a buyer paying a great deal of money for a blade needed a way to tell what he was holding. In the 11th century, the polymath Al-Biruni wrote a book on precious stones and metals containing a recipe for making crucible steel. 2 other medieval recipes survive, and what makes his unusual is one ingredient in the charge, a substance called rusek-taj, which modern scholars could not identify. European interest in the Indian steel is usually dated to the 1790s, when ingots of it reached London and were handed to chemists. Their timing was good, because the underlying chemistry of steel had only just been worked out. Torbjörn Bergman in Sweden had shown at the start of the 1780s that cast iron, steel, and wrought iron differ from one another only in how much carbon they contain, with cast iron holding the most and wrought iron almost none. So the chemists came to Woots, already knowing that the answer would have something to do with carbon. Michael Faraday, whose father was a blacksmith, worked on the problem in the 1820s with James Stoddart, a maker of surgical instruments and a cutler. They analyzed the Indian steel, found traces of alumina and silica in it, oxides of aluminium and silicon that are ordinary constituents of sand and clay, and concluded that these were responsible for its properties. Faraday and Stoddart then went on to alloy steel deliberately with platinum, rhodium, silver, and nickel. In the first sustained program of alloy steel research anyone had conducted. At the Russian arms works at Zlatoust, a metallurgist named Pavel Anisov spent years on the problem and did reproduce the pattern, publishing his methods in 1841 in a monograph that was translated almost at once. Like every smith before him, he could not say why the pattern appeared. Then, in 1924, a metallurgist called Zschokke got permission to cut into 4 genuine Damascus blades from a collection assembled by the Swiss traveler Henry Moser, now held in the Bern Historical Museum. 3 of the 4 turned out to be woots, and Zschokke published the first careful account of what is actually inside such a blade. Carbon ran to nearly 1 8/10%. Carbides lay in bands. His measurements were correct, and they explained nothing, because the composition of the blades gave no reason for the carbon to arrange itself that way. An explanation arrived through a partnership formed in the 1990s. Alfred Pendray was a bladesmith and farrier, a shoer of horses in Florida, who had been trying for years to reproduce woots from the historical descriptions. He melted his own steel in small crucibles and forged it out. He had real patterned blades to show for it, and no idea what put the patterns there. John Verhoeven was a professor of metallurgy at Iowa State University, with electron microscopes and a laboratory. Those two, later joined by the steelmaker William Dawksh, spent most of a decade on the question. Their first problem was that Pendray's success was intermittent. Some melts produced beautiful patterns and some produced nothing from the same procedure. That difference turned out to lie in his starting material. His successful melts had all begun from a high-purity iron and carbon alloy called sorrel metal, smelted from the ore of a single deposit in Quebec. Pure, in a commercial sense, means that nobody added the elements steelmakers normally add on purpose. It does not mean nothing else is in there. Sorrel metal carries a trace of the metal vanadium, at a few hundredths of 1%, inherited from the deposit it comes out of. That trace is what makes the pattern. Verhoeven and Pendray established that a small addition of certain elements, ones that readily grab carbon and lock it into carbide, will produce bands in a steel that otherwise would not show them, and that vanadium is the most effective of those elements. A few hundredths of 1% is more than enough, and the pattern appears with as little as 40 parts per million, 4 atoms of vanadium in every 100,000 of iron. Then they analyzed authentic Woots blades from museum collections. 6 of the 7 carried vanadium at or above 40 parts per million. The 7th had almost none, and carried instead an unusually high level of manganese, which is another of the elements that will do the job. When a cake of steel freezes in the crucible, it does not freeze uniformly. It grows dendrites, branching tree-shaped crystals of relatively pure iron, and the impurities are pushed ahead of the growing branches into the liquid that has not frozen yet. So the last metal to solidify, in the spaces between the dendrite arms, is enriched in everything the dendrites rejected. Vanadium ends up concentrated in a network of thin films threading the spaces between those arms. None of that network is visible yet. Forging brings it out. A smith heats the cake and hammers it repeatedly over many cycles, and the temperature of those cycles is the critical variable, because the metal has to be worked below the temperature at which all the carbide dissolves back into the iron. On every cycle, then, carbide particles partly dissolve and then grow again as the metal cools, and the larger particles grow at the expense of the smaller ones. The boundary between a carbide particle and the iron around it is not a fixed line. It is a front, and it moves whenever the particle is growing or dissolving. In the vanadium-rich films, Verhoeven and Pendray propose, the vanadium atoms sitting in its path slow that front down. So carbide there resists being dissolved away on each heating and survives to grow larger on each cooling, while carbide in the leaner metal goes back into solution and comes out fine. They offer that step as a model rather than a settled result, and a rival account is under discussion in the same literature. After many cycles, the carbide in the vanadium-rich regions has coarsened into large particles, while the carbide elsewhere has stayed fine. And the hammering has flattened the whole network into the sheets that lie along the blade. What the smith could see of this was heat and time. Work the steel too hot, and the record of where the vanadium collected is wiped out, and the pattern never comes back, which is what happens when a Damascus blade is reforged carelessly. Good blades also carry a great deal of phosphorus, picked up from the ore. Phosphorus makes steel hot short, meaning prone to crumbling under the hammer at forging heat. So the usable range of temperature was narrow, and the smith had to burn the carbon out of the outer skin of the cake to decarburize it, so the surface would hold together while he worked. That is transmissible craft knowledge. What was in the cake could not be taught, because nobody along the route could see it, not the smelter in India, not the merchant, not the smith in Isfahan in central Persia. This is the shape of Verhoeven's hypothesis about how the technique was lost. Suppose that for several centuries, the cakes arriving from India came from ore bodies, underground deposits, that happened to carry the right traces, and blades with good patterns were being made. Then suppose the source changed. A deposit is worked out, or a merchant switches suppliers, and the cakes keep arriving, and they feel the same under the hammer, and no pattern appears in them. Every smith in the trade is doing exactly what he was taught. There is nothing to correct, because the error is not in the process, and any one link in the chain could fail without the others noticing. Within a generation, the men who had made patterned blades are dead, and their apprentices have learned a procedure that no longer produces a pattern. The finest blades date to the 16th and 17th centuries. The last of the high-quality patterned work was probably made around 1750, and lesser patterns persisted into the early 1800s. When the smiths at the Paris Mint tried to make the steel in the 1820s, they had the right carbon content and the wrong trace chemistry, and vanadium had not yet been accepted as an element at all. That came in 1830. A site in Iran called Chahak complicates that picture. The excavation there, published in 2020 by Rahil Alipur and colleagues, found the only crucible steel workshops so far identified inside Iran, radiocarbon dated between the 10th and the 12th centuries. In the slag, under an electron microscope, they found the remains of chromite, an ore of chromium, and in the little beads of steel trapped in the slag, they measured chromium at 1 to 2% by weight. Chromium at that level is not a trace. It is a deliberate bulk addition, hundreds of times the quantity of vanadium that makes bands, and the excavators argue that it identifies rusek-taj, the ingredient in Al-Biruni's recipe that nobody could name, which they read as chromite sand. If they are right, somebody was adding a chromium mineral to steel on purpose, from a written recipe, about 800 years before anyone else is known to have done it. That same study reports that the trace elements at Chahak, vanadium among them, were unintended impurities that came along with the main ingredients and turned up only sporadically. The Persian workshop knew what it was putting in the pot at the level of percent and remained as blind as everyone else to the level of parts per million. There is also a 13th century Persian manuscript which records that Chahak steel took a fine and exquisite pattern, that Chahak swords were brittle, and that the brittleness cost them their market. In 2006, a group at Dresden led by Marian Reibold obtained a sample from a 17th century sabre attributed to the smith Asad Ullah. It came from the same Bern museum that had supplied Zschokk's blades 80 years earlier. They dissolved part of the sample in hydrochloric acid to remove the iron and leave the carbide behind. Then put what remained under a microscope powerful enough to image individual atoms. They reported nanowires of iron carbide, and around them, carbon nanotubes, cylinders of graphite a few nanometers across, about 10 atoms wide. Nanotubes had been a central object of materials science since the early 1990s. Their report ran in the journal Nature as a single page, a brief announcement rather than a full study, and the press coverage was very large. And what spread was the idea that medieval swordsmiths had been unknowingly practicing nanotechnology. Metallurgists did not change their account of the bands. When Verhoeven and Pendray published a review of the whole problem in 2018, going back over the reproduction work and the mechanism, they set out the vanadium account again. The bands are about 10,000 times coarser than a nanotube. The legend rests on a claim about performance. These blades were said to cut a silk scarf falling through the air, to shear through European swords, and to hold an edge no other steel could hold. Modern replication makes that testable, because bladesmiths now make woots to the historical composition on purpose, and the results can be put through the same mechanical tests as any other steel. A recent characterization of a woot's blade at about 1.5% carbon found its hardness, meaning how well it resists being dented, in the normal range for a well-made carbon steel. Its edge retention was good for a steel of that kind, about equal to the best of the ordinary low-alloy steels, and behind the modern alloys built around chromium and vanadium for wear resistance. Its toughness, meaning how much abuse it takes before it cracks, was the worst of the group it was measured against at equal hardness. The swordsmiths were being judged against the alternatives available to them, and against those the material is excellent. A medieval European blade was typically a composite, soft iron with a little hard steel welded on at the edge, and the quality of the weld and of the steel varied a great deal from blade to blade. Set beside that, an object that came out of a single melt, the same metal all the way through with no weld in it to open up, was an extremely good sword. The pattern was information. A smith could not analyze a cake of steel, so he read its face instead. The bands are a direct record of how the metal froze, which is a record of the chemistry of the melt, and so of an ore body in the Deccan, the highland interior of southern India, or on the Iranian plateau. Fine watering meant that everything upstream had gone right, and the whole industry, from a pit of crucibles in India to the sword market in Isfahan, had agreed to treat that visible signal as the standard for a product whose real chemistry nobody could measure. A tradition can be transmitted perfectly, every step of it correct and complete, and still stop working, because part of what made it work was never in the instructions and never could have been. The smiths who forged these blades knew everything about making them except what was in the metal, and that was fixed for them, before any of them touched it, by the geology of a place they would never visit.